Now let's see about lens makers formula. Suppose if you take a thin lens, one side radius of curvature R1 and other side radius of curvature R2. So they place this lens in a medium of refractness mu1, and the lens refractness is mu2 you can assume. And of course this again come into same media, so refractness is mu1. So this is the principal axis. You can take principal axis. Suppose if object is at a particular distance, somewhere here is the object O, which is u distance from the optic center P, and this is the incident ray. Because of medium changes and this refracting curve, what happened? It bends, so it refracted like this. Where it meet the principal axis, there it forms image. You can think, yes, there it forms the image. This is image dash. Why? Because that is not final image, but because the ray is modified by only first refracting surface. Again this ray is modified here when it hit on the second surface, it modified and it get again refracted and it forms a final image somewhere here. That final image you can name it as I. So what is the distance of the first image formed by only first refracting surface? That is a distance V1 you can think from here to here, and final image distance, that is you can take it as V from final image to optic center. So two images we are assuming, but that image will be modified and forms as a final image. So we didn't find two images, we are observing finally only one image that will be modified and forms here. That means for first refracting surface, this is the object and I dash is the image. For the second refracting surface, I dash is the object and I is the image. But because that only modified, that's why I dash is the object for second refracting surface. And write the relation of refraction at curved surface. Suppose if you take this is a curved surface and here object distance is u and image distance is v, and refractness here mu1 and mu2. Light ray enter from first medium to second medium. What is the formula you get? Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. That we derive refraction at curved surface concept. Similarly, we can apply third formula for two refracting surface. First, we can apply for first refracting surface R1. So for that, what you can write? Where to where light enter from mu1 to mu2 medium. So we can write mu2 by v1. Why? Because due to first refracting surface where image forms at I dash, nothing but v1 distance, minus mu1 by u is equal to mu2 minus mu1 by r1, first refracting surface over. This is equation number 1 you can take. Now second refracting surface. For second refracting surface, light ray where to where we are taking? Light enter from mu2 to mu1 we are taking, reverse. Here mu1 to mu2, then mu2 to mu1, lens to outside. So what is the distance of the object? For the second refracting surface, v1 is object distance, v is the image distance. So you can write here mu2 final, it comes into mu1 by final image distance is v, and minus mu2 by v1. In place of object distance, now what you get? v1 we are getting, image, final image we are getting, is equal to mu1 minus mu2 by r2. Reason you know, last time it entered from 1 to 2, now it entered from 2 to 1. So final minus initial. So here final is mu1, initial is mu2 for second refracting surface. Add these two equations. If you add these two equations, what you get? You see 1 plus 2. These two terms get cancelled and we get right mu1 common. Mu1 common 1 by v minus 1 by u. We get left side. And what you get right side? Here mu2 minus 1 mu1. Here also take mu2 minus mu1. Take minus here. That what you get mu2 minus mu1 common into 1 by r1 minus 1 by r2 you get. But we know lens formula. What is lens formula? 1 by f is equal to 1 by v minus 1 by u. Using this formula, you can replace this 1 by v minus 1 by u as f. Send this mu1 this side. What do you get? 1 by f is equal to mu2 minus mu1 by mu1. Take mu2 by mu1 minus 1 into 1 by r1 plus or minus. You can take general equation r minus 2. Depend upon the type of the lens we are using here, that is here double convex we are using. Sometimes you can use concave or sometimes they use convex or concave, like that. Different type of lenses we are using, and the sign conventions of R will be decided based on the type of lens. For example, and convex lens, both sides convex is there, double convex. Then here this also plus and this also plus. All are plus you have to take with respect of this sign. Don't take this general equation and don't take this sign, and take only plus for convex means. Suppose if you take a lens which is like a lens concave lens. Concave lens means both minus, here and here minus, here also minus only. Okay, don't consider this minus, both minus, that's it. Final value minus 1 by r1 minus 1 by r2 is for concave. Suppose sometimes you can take a convex surface and this side we get concave surface. In this case what happened? For first refracting surface r1 is positive and r2 is negative, because from this side is concave. From outside you have to check convex and this side concave. That's why plus, and this you can take it minus. Suppose you can take this formula here. There is a lens which is having refract index of mu and placed in air. Air nothing but mu, air is 1. So refractive index is 1. In that case what you can take? Mu2 is the refractive index of the lens and mu1 is the refractive index of the medium, in which medium it is placed. Here that is 1. Then what you get? 1 by f is equal to mu minus 1 by, because mu2 is mu and mu1 is 1, minus 1 into 1 by r1 minus 1 by r2 we get. This is the lens maker's formula when the lens is placed in air, that you can take it as f air. Suppose how this formula will be modified for different type of lenses, that we'll see now. Suppose you can take a double convex lens. So you can take a double convex and radius r1 and r2. Then how to write means 1 by f is equal to, here outside air and inside refractness mu. Then you can write mu minus 1 into 1 by r1 plus 1 by r2. Simply forget about here whatever the sign. Take convex means plus. Okay, like this we can write. Suppose if it is equiconvex, r1 is equal to r2 in this case. R1 is equal to R2, the first case you can take. Here if R1 is equal to R2 is equal to R, then what you can write? 1 by R plus 1 by R. You can write 2 by R. So F is equal to R by 2 into mu minus 1 we can write. So for equiconvex lens, focal length formula like this we can write. Generally for concave mirror means what you get r by 2 only, but here and for lenses it is a different formula here, r by 2 into mu minus 1. Suppose plano convex. Plano convex means one side flat surface is there. Then what you get this formula. Second one, plano convex. R is there and the other side infinite. Then what you get this formula, f is equal to r1 by f is equal to mu minus 1 into 1 by r, and 1 by r to become 0, infinite now, that's why you can write like this. So f is equal to r by mu minus 1 you get for plano convex. Same thing if it is a concave, double concave, then what you get here, both minus you are getting, this minus and this minus you get, both minus you get, and here also you get minus. Plano concave, r and infinite, then what you get here, you get minus, this you get minus here, minus 1 by r, and that becomes 0, like that. Suppose lens is initially in air, now if you are placing in a medium, then what happened to focal length, that we'll see now. Initially it is in air, so what is focal length formula, you can take like this, this formula, f air is a mu minus 1 into 1 by r1 minus 1 by r2 we can write. Now suppose if it is in a media, f1 by f in a media, I'll write fm, focal length of the lens when it is placed in other media, that we can write mu of the lens by mu of the liquid nothing but medium here, minus 1. Why? Because lens maker's formula mu 2 by mu 1. Mu 2 is refractiveness of the lens, by mu 1 is medium. Here medium different is there. In first case it is air, that's why 1. Here different. Thus we can take like this into 1 by r1 minus 1 by r2. And divide these two equations, 1 by f air by 1 by f medium. So we can write f medium by f air is equal to what we get here, mu minus 1 by mu minus mu medium into mu medium we can take. So what do you get relation between focal length of the lens in air and focal length of the lens in a medium? Then we can write f medium by f air is equal to mu minus, mu is the refractiveness of the lens and mu medium is in which medium that lens is placed. So here what happens if mu, first case, mu is greater than mu medium. If mu is greater means what happens, the focal length focal length increases. So f medium increases, f medium is greater than f air. So nature of the lens is not changing. Suppose if you take a convex lens, what do you say? It is positive lens or converging lens. Concave lens means it is a diverging lens. So nature of convex converging lens and a concave diverging lens is not changing. Still it is behave like a convex, behaves like convex only, concave like a concave only, it behaves. Suppose what happen if second case, if refractiveness of the lens is equal to refractiveness of the medium, then what happen? Both equal, here denominator becomes 0, then what do you get? It becomes infinite. So then focal length in the medium is equal to infinite. That means light is not bending. So here there is no converging point. So why? Because both refractiveness are same, is medium is same. When medium change is not there, there is no bending of light. Converging or diverging not possible. Suppose third case, if refractiveness index of the lens is greater than refractiveness of the medium, then what happen? So if it is greater means what I get, this you get a reverse sign. Here you see negative we are getting. That means in before, and this lens is like a convex lens. Once it immersed in a liquid or in a medium which is having refractiveness greater than mu is less than mu medium, then what happen? It changes nature. Convex behave like concave and concave behave like convex. Example, an air bubble nothing but like a sphere. Sphere nothing but we can think like a convex lens only. So but it behave like a concave lens inside the water, because water has more density, that medium has more density when compared to lens made with air there. So that's why it behaves like a diverging lens, it behaves like a concave lens. So in that case, if mu is less than and mu is less than mu medium, what happen? The nature of the lens become reverse. Converging become diverging, diverging become converging. Now see for a lens, and here mu refractive index is mu1, lens is made with mu2, and other side refractive index is different. Suppose a different refractive index is there, and lens maker's formula we derive here, and this total medium is same and lens medium is different. Here three different mediums are there. At first mu1 medium, mu2 lens, mu3 again outside other side medium. So in this case, object is placed at u distance, and due to first refracting surface forms at I1, that will be modified by the second surface and forms at I. So formula, lens maker's formula we can apply normally we can apply, that is mu2 by v1 minus mu1 by u is equal to mu2 minus mu1 by r1. That is first formula. Second formula, here where to where enter, it enter from mu2 to mu3. So what you can write, mu3 by v minus mu2 by v1, that is a is equal to, here what you can write, mu where to where it enter, there last time 1 to 2, that's a 2 minus 1, here now 2 to 3, so that's why I can write a 3 minus 2 by R2 we can write. Now add this, so what do you get here, if you add mu3 by v minus mu1 by u is equal to mu2 minus mu1 by r1 plus mu3 minus mu2 by r2 we get. If mu3 is equal to mu1, and same formula what we get, lens maker's formula we get from this. Okay. Different mediums are there here, and first media, second media, and third media. Different mediums, so you get like this. Now let's see about power of the lens. Suppose you can assume a lens, and this is the principal axis. If a ray which is passing parallel to the principal axis, suppose this height you can take, this is the center of the lens, nothing but optic center. This height you can take it as h is equal to 1 meter. The ray which is going parallel to the principal axis must converge at its focus. Distance between these two is f. Small f. Suppose if this angle you can take it as delta. The ray which is going parallel to the principal axis, which is 1 meter distance from the optic center, this height is 1 meter. And what is a tangent angle? What is tangent angle? That they call it as optical power. P is equal to opposite tan delta is equal to h by this distance, that is pf or f we can take, which is equal to 1 meter. So you can write as 1 by f. So what we can define optical power, nothing but power of the lens. It is a reciprocal of focal length. Or otherwise, what is the tangent angle made by the refracted ray with the principal axis when it is refracted from 1 meter distance or unit distance from the optic center. And what are the units? SI units, let's see, units of power is diopter. Represent with capital D, or you can write meter inverse. Why? Because the reciprocal of focal length. Focal length generally they measure in meters. SI means CZS means centimeter inverse we can write. So simply, what is a focal power or power of the lens? It is a reciprocal of focal length of the given lens. Units diopters and meter inverse, CGS units means centimeter inverse you can write. Now we'll see combination of lenses. Suppose you can take two lenses are in contact. Focal length of first lens is f1 and focal length of second lens is f2. This is a common principal axis for the both lenses, and initially object is at a particular distance, u distance from the lens. Think that these two are thin lenses. There is no much difference. Here is the optic center P. We can take the ray enters into the first lens and it gets refracted. So because of refraction, it will be form image here that you can take it as I dash. But because that refracted ray again modified by the second lens, so this will be modified and forms final image here I. Take that object distance is u for first lens, and what is image distance? I dash is the image, so that you can take it as a v1 or v dash. That is the image distance of the first lens. And what is the object distance of second lens? This will be modified and final image forms here. So I1 is the object for second lens and I is the image. So what is object distance for second lens? That is V1 is the object distance and V is image distance. So here that image modified and again it will be replaced here. That gone and this created here. Now apply lens formula. What is lens formula? 1 by f is equal to 1 by v minus 1 by u. Using that for first lens we can apply 1 by f1 is equal to, and where image forms, that is at I dash, that is 1 by v1 minus 1 by object distance is u. This is equation number 1. For second lens we already discussed I dash is the object and I is the image. So in that case 1 by f2 is equal to, what you can write, 1 by v, image where it forms at v distance, where object, that is v1 is object distance, minus 1 by v1. This is the second equation. If you add these two equations, then what you get? 1 by f1 plus 1 by f2 on left side, and right side what you get? 1 by v1, here minus 1 by v1 get cancelled, and what you get? Finally 1 by v minus 1 by u. You see what is u? Object distance, and what is v? Finally where image forms. So that gives a resultant focal length. In place of this we can write a focal length of the combination f net is equal to 1 by f1 plus 1 by f2. This is the combination of the two lenses. What is the net focal length? 1 by f1 plus 1 by f2 when they are in contact. Of course, depend upon the nature of the lens. Here both are convex lenses, take positive value. Suppose sometimes if you take one is convex, other is concave, then take one is positive, other is negative. So like that we can apply sign convention also. Suppose you can take here some distance is there, distance between these two lenses is there. Now first lens have focal length f1 and second lens have focal length f2 and distance between them is d. Then how we get resultant focal length means 1 by f net will be modified like this, 1 by f1 plus 1 by f2 minus d by f1 f2. This is the formula when two lenses are separated by a distance. So in contact and separation, d equal to 0 means that only we get here. Similarly, how we get focal power? Focal power of the combination. First we'll see reciprocal of focal length. What do you call focal power only? So from here, from this equation, what you can write? P net is equal to, net power is equal to P1 plus P2. And here what you can write, P net power of the combination of these two lenses which are separated by d distance, that is 1 by f1 is P1, 1 by f2 is P2 minus d, 1 by f1 is P1 and P2. You can write this is the focal length of the combination of two lenses in contact and they have some separation d distance means. Now see different applications on combination of lenses. For example, we can take is a equiconvex. What is the focal length of equiconvex? We already discussed about that. That is f is equal to r by 2 into mu minus 1. Mu refractive index and radius of curvature of both sides. Suppose what happen if you cut this lens and like this perpendicular to principal axis, then it become two plano-convex lenses. It become this side radius of curvature is r and refractive index same. Then what you get, focal length f dash is equal to r by mu minus 1, because one side curvature is infinite, r is equal to infinite. There two sides are, here one side infinite, one side r. So what is the relation between that focal length and this focal length? That become 2f. That means if you cut a lens perpendicular to principal axis like this, what is the focal length of the one of the piece? That is 2 times of this we get. Suppose if you join these two pieces, suppose two pieces are there like this, two plano-convex we are getting. Suppose if those two pieces if you are joined like this, again if you join like this, then focal length becomes same as this. This is 2f. We already calculate 2f with using formula 1 by net focal length. 1 by net focal length f net is equal to what you can write, 1 by 2f plus 1 by 2f. Nothing but 1 by f we get. So what you get, net focal length you get same as f initial focal length if you separate and again join. Not only like this, even if you join like this with two curved surfaces contact each other. Last time two plane surfaces in contact. In this method also we are getting same focal length, or otherwise you can take a combination like this, one after other, like this also. So in all the cases the focal lengths are 2f and 2f for each plano-convex lens. After combination what you get, this you get focal length f, same as that. This also you get focal length f. Second case, suppose you can take an equiconvex lens and radius of curvature r and r, focal length is f, and what is the formula for focal length of equiconvex lens? R by 2 into mu minus 1. Suppose if this lens is cut parallel to principal axis, if the lens is cut like this, so now what is the focal length of each part of the piece? Suppose you can take this part of the lens and this part of the lens. If you take separately, in this case there is no change in the focal length. Why? Because medium is not changing. Here refractness mu means here also refractness mu. Even you can take here radius of curvature, here radius of curvature, both are same. And what is the radius of curvature of the lens? Suppose this side you can take it. You can take this total part, or you can take a small portion. Suppose you can take a small portion which is cut from this. Suppose if you take this small portion, what is the radius of curvature means? This side R1, this side R2 only we can take. Okay, so if you cut parallel to the principal axis, there is no change in radius of curvature. So due to that, there is no change in focal length. Here F means here also for each part it is F only. Suppose if these two parts we are arranging one after other. Suppose if you take first one like this, one part of the lens, and next again if you take another part of the lens, this is F and this also F. And what is the net combination? We know F net is equal to 1 by F plus 1 by F. From this what you get? F by 2 it become. Focal length become half of the initial. If they take two combination, both combined means. So on splitting like this, there is no change in focal length. Not only this, you can take a small portion. Suppose you can take this part outside. This part outside I draw here a small portion like this. A small portion of the lens. What is the focal length? Focal length is no change in focal length. It will be same as F. That is R by 2 into mu minus 1 only. There is no change in focal length. Because mu is same, medium same, and curvature is also same. Only aperture. Aperture means this vertical height, what we call aperture. Aperture decreases, but there is no change in and focal length. Suppose in previous case, if you cut perpendicular to principal axis, what happened? Focal length changes. That means where distance of the image also changes. Here, if you cut like this, distance of image is not changing. Suppose instead of two pieces, if you are using one, or otherwise if you are using the small piece, there is no change in the position of the image, but brightness of the image changes. But because initial aperture size is more, whatever the rays fall on that, all are converging at that particular point. But now what happened? A small amount of light rays which are fall here, that only converges. Of course, converging point is not changing, focal length not changing, but the brightness of the image changes because of number of rays converges or diverges or decreases here in the second case. And this combination, yes, of course, focal length changes because two lenses, you can think like a series combination of F and F. In series combination, we get F by 2 is the net focal length we get. Third case, we took a lens which is made with a different type of material. Suppose up to here one type of material, here different material, here different material, and here different material. Suppose for example this part is made with a material which is having refractive index mu1, and next one made with refractive index mu2, and next one you take mu3. Again here this made with refractive index mu1 again, or maybe take it that is a different refractive index. This is made with mu2. In this case, how many number of images are formed? The number of images formed, so you can take this the principal axis. So these two materials are same, these two are forming image at a particular point. So the rays which are coming from these two regions are forming image somewhere here. So this is the first image we get. Now these two also same materials, mu2 and mu2, so focal length is same. Those two forms image somewhere, maybe beyond this or below this, depend upon the refractive index value. So it can form image somewhere here, that is second image. And this third material can form image somewhere here. So three different images we are getting, three different images, because three different materials are used in the making of lens. Suppose like this, if you make a lens, if they made a lens like this, first material, second material, third, fourth, fifth and sixth. Different materials means long principal axis, first material forms at one point, second material forms at other point, third material forms at other point, maybe fourth at different point. So each material forms images at different points, and this lens is having different focal length for each material. Due to that, what happened? Different images we are getting. How many number of images we are getting? That is 6 number of images we are getting. Here we get 3 number of images because three different materials are there. Suppose out of these any two are same. Suppose 2 and 5 materials both are same. Both are same material, and those two commonly form a single image. So 1, 2, 3, 4. This also forms as 2 and 6. Total 5 images only we get in that case. Only 5 images if these two are same. So same type of material means, and radius of curvature of this side is same for all the materials. This side also same for all the materials. So radius of curvature is not changing because of change in nature of the material. Focal length changes. Due to that, different images they form. In the same case, suppose if you made lens like this with a different material. Suppose this side they made with material which is having refractness mu1, and the other side they made with a different material which is having refractness mu2. Here we are not getting two images, we are getting only one image. Why we are getting one image means, you see that due to first lens, that is first half lens, you can take first plano-convex forms image somewhere, that will be taken as object by the second part of the lens, and again it modify the image and it shift the image position nearer or far away depend upon the value of mu value. Okay, here how many images we are getting? Only one image. So example, you can take this object and here it try to form image. Then what the lens is doing? It try to form image somewhere here. What second lens is doing? That will be modified. It forms image somewhere here. This is I dash and I. This type of cases we discuss. A refraction and a combination of lenses also we discuss. Only one image we get here. Only one image. Suppose if they give another application, so you can take here. This is a lens made with three different material. Three different material means see, half of the material is mu1 or mu3 is there, this one, and remaining two materials here half is made with mu1 and second half is made with refractness mu2. This material is different. Then how many number of images are formed? And this is the principal axis, you can think. And due to mu3 directly we get one image here, that is a third image. And due to third material. And due to first material, whatever the rays we are getting, that will be try to form somewhere here. That will be modified by the second and it forms at other point. So here like this. So here actually you get two images only, that is due to first material it forms, that will be modified by the second material, that only. So here how many images we are getting? Two images. That means if the materials or lenses connected in series or arranged in series, that image will be modified and finally forms single image. Suppose if you are taking materials are parallel, so how many materials are there in the parallel? That many images are formed. That we have to remember here, important point. Here one image, there two images. Of course, and three materials are there, but the image formed by the first material modified by the second material or second lens here. So finally, due to these two get one image, and due to this material we get another image. So total we get two images there. Fourth case is, suppose if n number of lenses are in contact like this. N number of lenses are there. Each have focal length f1, f2, f3 and powers p1, p2, p3, so on. Power n and focal length of nth lens. What is the combination? Net focal length of all the combination. If in contact, net focal length formula is there. Two lenses are in contact, 1 by f1 plus 1 by f2. Same formula we can use here. 1 by f1 plus 1 by f2 plus 1 by f3, so on 1 by fn we can write. Combination of the lenses and net focal length. Suppose focal power, if you want net focal power is add sum of all the focal length, p2 plus p3 plus so on pn. Net focal length we can write, net focal power we can write like this. Now see fifth case, that is a combination of a mirror and a lens. For example, you can take a plano-convex lens which is having radius of curvature r, refractive index mu. Then what is the focal length here? Focal length of this lens f is equal to r by mu minus 1. What is the focal length of this lens? When you coat this side with silver coating is there, that means it behaves like a mirror, and we are coating silver on flat surface, so it behaves like a plane mirror. Then this we can write like this. This we can write like this. There is a plano-convex. After plano-convex, light enters into that. After entering into the plano-convex, it fall on a flat mirror. So it is a combination of a plane mirror. After reflection, what happens? It again travels through plano-convex and comes outside. So again, it will be taken as a plano-convex. What is the focal length of this? That is, focal length of this is f. Focal length of the plane mirror is infinite, and focal length of this again it comes into the same length. That's why f. So how to write combination of these two? Combination. So we can write f net is equal to f net is equal to 1 by f1 plus 1 by infinity 0 plus 1 by f2. Nothing but f2, f1, f2 both are same. So you get 2 by f. So f net is equal to f by 2. But where final image forms means it behaves like a concave mirror. Why? Because you see the light ray enter inside and reflect back. Suppose here light ray enter, it will be refracted like this, and it comes outside, and like this it comes. So image forms on same side of that. That is a real image. Here it is forming. A real image means what you say here, it is behave like a concave mirror. Why? Because an image forms same side means we can take mirror, and that to real image. So it behaves like a concave mirror of focal length f by 2. The same thing, suppose if you take a double convex or equiconvex, you can think. And what is the focal length formula? R by 2 into mu minus 1. Suppose one side of the mirror is silvered. One side of this is silvered. Then this combination we can write like this. That we can write first it enter into convex lens. The light ray enter into convex lens, and it reflect on curved surface and reflect back, and finally comes outside. So in this case, how many lenses are there? One convex lens of focal length f plus one concave mirror. You see this side is concave, it behaves like a concave. Here flat mirror, here concave mirror. What is the focal length of this concave mirror? That is r by 2. R by 2. Reason you know for concave mirror, what is the focal length? Half of the radius of curvature. Plus again after reflecting, what happened? It comes outside through the lens. So again it uses the lens. That's why again you can take another combination of the lens f. Then how to take a combination of these three lenses? That is 1 by f net is equal to 1 by f net is equal to, here f nothing but, here that you can write 2 by 2 into mu minus 1 by r. Reciprocal of this you have to take. 1 by f we need. plus this one 1 by f1 plus 1 by f2. What is f2? 2 by r plus finally for this same as that is 2 into mu minus 1 by r. So add numerator and LCM is same for all. F net is equal to r in denominator. Numerator what you get here? That is 2 mu, here 2 mu, 4 mu, minus 2, here plus 2 is there. So what do you get? And minus 2 remains. That we get in numerator. Otherwise it is better take 2 common. So we get F net is equal to R by 2 common 2 mu minus 1 we get. This is the net focal length we get. This also behave like a concave mirror only. Why? Because image of parallel beam is parallel beam of light is fall on that first converges and again it will be reflected back and comes into the same side, it forms a real image. So in this case it behaves like a concave mirror. Image forms the same side, that to real image. So convex means it never forms a real image. So it behaves like concave mirror. Suppose you can take a lens, so equiconvex lens, radius of curvature is r both sides, focal length f, that we know focal length formula it is r by 2 into mu minus 1. We have formula like this, and this is a principal axis. So principal axis, suppose if you cut this lens into two parts parallel to principal axis, it behaves like two separate lenses, and this is one part and this is other part. Suppose if these two parts are separated like this, so this is first part and focal length is not changing. If you cut parallel to principal axis, focal length is not changes. Already we discussed that this has focal length f, this also focal length f. There one principal axis is there, but now here what you get, for this you get a principal axis like this, for this we get another principal axis we get like this. For example, here initially you can assume an object is there. Now that object here it is not moving because of motion of the lens. Suppose if lens is moving like this, that is velocity of the lens in vertical direction, that is in y direction, and simultaneously this lens is moving like this, this lens is going like this, that means velocity of the lens in this direction is VLX. Then how image is changing? So either object is moving or lens is moving, the distance between object and lens is changing. So due to that definitely, and the velocity of the image also changes. We already discussed what is the velocity of the image. Velocity of the image in y direction is equal to y direction, nothing but vertical direction. Vertical direction you can say transverse motion. Transverse motion means what is the formula? M transverse into velocity in the direction, that is Ly. Velocity of the lens in vertical direction. This is the velocity of the image in vertical direction. MT is transverse magnification. So this formula only we can modify. Iy is equal to V by U. This magnification MT is, we can write V by U into velocity of the lens in vertical direction we get. Image distance and object distance, these two. Now if what is the horizontal displacement, horizontal velocity, that is velocity of the image in x direction parallel to principal axis. Suppose if lens is moving like this, and what is the velocity of the lens along x-axis, that velocity is same as the relative velocity of the object with respect to lens. Why? Because object is at rest. So we can write that, you can write mt square into velocity of the object, nothing but here velocity of the lens along x-axis. So this only velocity of the image along x-axis is equal to This we can write v by u whole square and this object distance and image distance into VLX. Same formulas we discussed already. If object is moving along principal axis, we are using this. Perpendicular principal axis, use this. But here only the difference, instead of object, lens is moving. Even lens is moving or object is moving, there is a separation between object and lens. So due to that, image also changes according to this. In combination of lenses, we'll see one case. Suppose if you take two convex lenses, and this radius of curvature is R1 and this is radius of curvature R2, is in contact with another lens which has here radius of curvature R3 and the side it is R4. So refractive index of this one is mu1 and this is mu2. So what is the net focal length of the combination? Net focal length of the combination we can write like this. For first one, what is the focal length? 1 by f1 is equal to, so outside air you can think, and mu air is equal to 1, and that's also refractive index is 1. So if the lens is placed in air, then what is the focal length? That is a mu of the lens, so mu1 minus 1 into 1 by r1 plus 1 by r2 we get. 1 by r1 plus 1 by r2. Similarly for second lens, what do you get? For second lens, we can take 1 by f2 is equal to 1 by f2 equal to mu2 minus 1 into, here radius of curvatures are r3 and r4, so you can write r3 1 by r3 sorry 1 by r3 and 1 by r4 we get. What is a net focal length? Nothing but we know net focal length formula, that is 1 by f is equal to, we can write 1 by f net is equal to 1 by f1 plus 1 by f2 is there. Here this also you can write reciprocal and write, and more variables are there, we get big equation. But here one special case, suppose what happen if the space between the lenses is filled, this space is filled with a liquid which has refractive index mu liquid, then what happened to new focal length? A combination of three lenses are there. One is and first convex lens and second convex lens, and the between these two the gap is look like a concave lens of one side radius of curvature R2, other side radius of curvature R3. So this becomes like a concave lens. This is actually R3. Now what you get, it is a combination of one convex lens of focal length f1 plus one concave lens. We don't know focal length, that you can take it as focal length of liquid lens or L. Next again another convex lens is there and focal length is f2. We know f1 and f2, we don't know fl. To calculate that, what is the focal length of the liquid lens? So general formula we'll take here. First of all, if two surfaces are there, 1 by f is equal to mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. This is the formula, general formula for lens makers formula. So here 1 by f liquid we need. For this lens we need focal length, remaining two we know. That is equal to mu2 with what medium that lens is made, that is mu L. Where it is placed, if these two lenses are not there, then you can think that it is placed in air, so that you can take it as 1 minus 1. After combination we can say, but don't take here mu1 and mu2, it is in air only, like you can take, then after combination we can write the total value. That is minus 1 by that side radius of curvature, this curvature is R2 and this curvature is R3 for this liquid lens. So what you can write, minus 1 by R2 minus 1 by R3. We already discussed what is sign convention. For concave mirror, for concave lens, both you have to take negative with respect to whatever they give here. Forget about that. Don't take total negative. Convex means positive, concave means negative. We can take. This is the focal length. F liquid is equal to what you get here. That you can write here mu liquid minus 1 into minus, if you want you can take minus common, 1 by R2 plus 1 by R3. Now what is the total combination of the focal lengths? So total resultant is F net, total of all these three lenses is 1 by F1, nothing but that, plus 1 by F liquid, nothing but this part, plus 1 by F2 we can write, that is second lens, focal length of the second lens. Suppose here if they gave a simplified question, that is radius of curvature all are same, R1, R2, R3, R4 all are same, means two double convex lenses are there, both are in contact and same medium, that is mu1 mu2 also you can take it as mu, and but only this is the different liquid. Then in that case how these cases are modified? So for this what we can write, 1 by F1 is equal to, we can write mu minus 1 by R, we can write into 2, and this one also 2 into mu minus 1. Why? Because same refractive index we are taking here in this, especially in this case, and here we can write R. How this we are getting? How this we are getting? That is minus of, here I'll write, it is minus of 2 into mu liquid minus 1 by R we get. So we're going to add these all, that is 1 by F net is equal to 1 by F net is equal to, so here 2 into mu minus 1 by R minus, for this 2 into mu liquid minus 1 into by R plus 2 into mu minus 1 by R we get. If you do LCM, that you get R, and what you get final value, that is here 2 mu, that is 4 mu minus 2 mu liquid, 2 mu minus 2 mu, 4 mu minus 2 mu liquid minus 2 plus 2 minus 2, so minus 2 remains there. That what you get net focal length. Suppose you can take reciprocal of this, F net is equal to R by, you can take 2 common, 2 mu minus mu liquid minus 1, okay, right, like this.